Lesson 10. Modern Atomic Theory. Objectives. Describe Rutherford's model of the atom. Explore the nature of electromagnetic radiation. See how atoms emit light. Understand how the emission spectrum of hydrogen demonstrates the quantified nature of energy. Learn about Bohr's model of the hydrogen atom. Understand how the electron's position is represented in the wave mechanical model. Learn about the chiefs of orbital designed by S, P, and D. Review the energy levels and orbitals of the wave mechanical model of the atom. Learn about the electron spin. Understand how the principal energy levels feel with electrons in atoms beyond hydrogen. Learn about valence electrons and core electrons. Learn about the electron configuration of atoms with Z greater than 18. Understand the general trends in the atomic properties in the periodic table. 1. Rutherford's model of the atom. Ernest Rutherford proposed the nuclear model of the atom based on the gold foil experiment. Key ideas of Rutherford's model. The atom has a small, dense, positively charged nucleus. Most of the atom's mass is concentrated in the nucleus. Electrons occupy the space around the nucleus. The atom is mostly empty space. Limitation. Rutherford's model could not explain why electrons do not spiral into the nucleus, how atoms emit light at specific wavelengths. This failure led to the development of quantum models. 2. Nature of electromagnetic radiation. Electromagnetic radiation, EMR, is energy that travels through space as waves. Properties of EMR. Wavelength, lambda distance between wave peaks. Frequency, new number of waves per second. Energy, E related to frequency. Relationship.
Okay, let me stop into here. Well, if you observe a wave, the light is an electromagnetic wave, so the distance between two peaks, this and this distance is what we call lambda. That is the wave of length. The frequency is the inverse of this. Then we can say that C, the speed of light divided by the frequency, is lambda. This is the relationship between lambda, or wave of length, times the frequency, and the frequency. And the energy is the constant of Planck times the frequency of the light. Let's continue then by the main idea, and let's see. Let's go here.
Key idea. Shorter wavelength, higher frequency, higher energy. Energy is quantized, meaning it comes in discrete packets called photons. 3. How atoms emit light. Atoms emit light when electrons move between energy levels. Process. Energy is absorbed, electron jumps to a higher level. Electron falls back to a lower level. Energy is released as light, photon. Each element emits specific wavelengths, producing a unique emission spectrum.
Okay, let me stop into here. Suppose that this is the nucleus of the atom, and let me draw here one level on here of energy, and here another level of energy. If a photon comes here, give the energy to the electron, and this electron jumps into the next level. If this is the energy of level 1, and this is the energy of level 2, we can say that the difference of these two levels is produced, or the electron can jump from one level to another with a higher level of energy because the absorption of the energy of the photon. But remember that the energy is quantized. Here, the energy has one value and here has another value. You don't have in between different values. No, the energy goes from here to this level of energy. Then, when the electron that is excited because absorbs certain energy from the photon that jumps into it, it can return to the original level emitting certain energy, and this energy can be calculated same way that I showed you before, because energy is equal to the constant of Planck times the frequency of the light that is emitted, and the spectrum is not continuous. The spectrum has lines, and every line represents a transition of one electron from one level to another level. Let's continue then here with the hydrogen emission spectrum. That is the simplest one, and I want you to learn it.
Hydrogen emission spectrum and quantized energy. The emission spectrum of hydrogen consists of distinct lines, not a continuous rainbow. What this demonstrates: electrons can only exist at specific energy levels. Energy changes are quantized. Each spectral line corresponds to a specific electron transition. This experimental evidence strongly supported quantum theory. 5. Bohr's model of the hydrogen atom. Niels Bohr proposed a model to explain hydrogen's emission spectrum. Main features: electrons orbit the nucleus at fixed energy levels. Energy is absorbed or emitted only when electrons move between levels. The model works only for hydrogen, 1 electron. Limitation: fails for atoms with more than 1 electron. 1. Energy levels and electron excitation. Electrons in atoms occupy quantized energy levels. To excite an electron, energy must be absorbed so the electron can move from a lower energy level, N, to a higher energy level, N2. For hydrogen, the energy of each level is given by
mayúscula E subíndice n igual a -2 y...
Okay, then the energy of each level is given by this formula. This is a constant, is the Rydberg constant, and here you have the level of energy that can be 1, 2, 3 square, and this energy is given in joules. Don't forget that. Then let's calculate the energy required for the excitation of one atom, of one electron, going from one level to another level. In general, we can see that the energy that is necessary is the energy of the final level minus the energy of the initial level. Delta E is positive because the energy must be absorbed during the excitation. Example, electron excitation in hydrogen problem. Calculate the energy required to excite an electron from level 2 to level 4. Look, here you have the two levels. Then, in a hydrogen atom, then you use the same formula for level 2 and the same formula for level 4. Then you have the difference of energy, delta A, delta E. The energy is this energy minus this energy. Then the energy that is absorbed, and that's why it is positive, is 4.09 times 10 to the 19th negative joule. This energy that must be absorbed to excite the electron is very, very important. According with this, when the electron returns to the original or base level of energy, emits a light, and this light has to be with the energy of the photon that is emitted. Then the energy of the photon is equal to the difference of energy between the two levels of energy. So, using this formula, where h is the constant of Planck, c is the c is the speed of light, that is also a constant, and lambda, that is the wave of length. Then you can calculate the wave of length of the light while the electrons returns to the basic level using this formula. The constant of Planck is this number. The speed of light is this number. And the energy that you calculated was this. This was the energy that was necessary to jump to a higher level of energy, and then it will be the same energy that will be released. So you can calculate lambda, and you can see that is equal to 4.86 times 10 to the minus 7 meters. Calculating, you can calculate or convert this into nanometers using the conversion factor, and you can see that is equal to 4.86 nanometers. If you go to the wave of length of the different colors in the spectrum, you can see that 4.486 nanometer correspond to the blue color. So you can say that ADC correspond to the blue-green cyan. This line belongs to the bulbous series of hydrogen. These are the different series in hydrogen. The series correspond to the difference to the different transition of electron from one level to another, and the corresponding light or line in the spectrum. Let's see this conceptual summary.
Conceptual summary, student-friendly. Energy levels in atoms are quantized. Electrons absorb energy to jump up. Electrons emit light when they fall down. The energy difference determines the wavelength, the color. Each element has a unique emission spectrum. 6. Wave mechanical, quantum mechanical model.
Okay, let's see. Here you can see the spectrum. This is a continuous spectrum, but in the atoms, what you get are lines. This is the emission spectrum, in this case for hydrogen. You can see here that the line that we observed was this, the cyan, yeah, that correspond to this 486 nanometer. Then you can determine which is the color, and you can determine the energy that correspond to this transition. Then everything, you can study the different transitions of electrons from one level to another level in the atom. Let's go now to the wave mechanical, quantum mechanical. Because this is, as I told you before, the theory that was studied by Bohr only can be applied to atoms that has only one electron. Then there is no interaction into electrons, and then this theory cannot explain the transitions in atoms that has more than one electron. That's why we use, in these moments, we use the wave mechanical or the quantum mechanical
Wave
model.
mechanical, quantum mechanical model. The wave mechanical model replaces precise orbits with probability regions called orbitals. Key concept. Electrons behave as both particles in waves. The exact position of an electron cannot be known. Instead, we describe where an electron is likely to be found. This is expressed mathematically by the wave equation. 7 orbitals and their shapes, S, P, D. Orbitals describe regions of high probability for finding electrons. Main orbital types. S orbitals. Spherical shape. Hold up to 2 electrons. P orbitals. Dumbbell shaped. 3 orientations, px, py, pz. Hold up to 6 electrons total. D orbitals. More complex shapes. 5 orientations. Hold up to 10 electrons total. Orbitals are not paths, they are probability clouds.
Okay, let me stop into here. Here you can see the representation of the orbitals. Here you can see the S orbital that is like a sphere, and here you have the P orbitals that are helicoidal in the 3 axes, Y, X, and Z. And the orbitals D that are more complicated, as you can see, and there are 5 types of orbitals. And let me stop into here. Orbitals are not paths, and you cannot represent as it was before that this is the nucleus, and then in level 1, in this orbit, you can find the electron. No, that's incorrect. What is exactly the position of an electron? Where is in a cloud? It's a region of the space where it's probably to find the electron. So this is for the S orbital, and these ones are for P, and these ones are for D. Remember that. Orbitals are not paths. They are probability clouds, regions of the space where it is probable to find the electron. Let's continue then. Let's continue. Then let's go here. You can see here the nucleus, and you can see the space where is more probable to find the electron. Let's go here to energy levels.
Energy levels and orbitals in the quantum model. Principal energy levels, n equals 1, 2, 3. Each energy level contains sublevels S, P, D, F. Energy generally increases with n. Within the same level.
S és menor que P, és menor que D, és menor que...
Okay, then you can see the energy of the s orbital is lower than the energy of the p orbitals, and this is lower than the d energy of the d orbitals, and this is lower than the f orbital. Okay? Then listen to this important
Electrons
information.
fill orbitals according to increasing energy. 9. Electron spin. Electrons have an intrinsic property called spin. Spin characteristics. Two possible values, plus 1/2 or minus 1/2. Each orbital can hold a maximum of 2 electrons. The 2 electrons must have opposite spins.
Okay, look at this. If you have, for example, let me represent the orbital S. I told you that is spherical. All this region is the most probably region where you can find the electrons. Where here you can have 2 electrons. One is spinning to the right and the other one to the left or opposite. And this is the representation of the spin of the electron. One is positive and the other is negative. One goes one direction, the other goes in the opposite direction, in order to avoid repulsion between electrons that are particle charged negative and negative. The 2 electrons must have opposite spins. Then let's go to the Pauli's exclusion principle. Listen.
This leads to the Pauli exclusion principle. No 2 electrons in an atom can have the same set of 4 quantum numbers. 10 energy levels in atoms beyond hydrogen. For atoms with more than 1 electron. Electron-electron repulsion alters energy levels. Sublevels split further. Energy depends on both n and orbital type. This explains why. Force fills before 3D. Transition metals have irregular configurations. 11. Valence electrons and core electrons. Valence electrons. Electrons in the outermost energy level. Responsible for chemical behavior and bonding. Core electrons. Inner electrons. Shield the nucleus and do not participate in bonding.
Okay, let's see. Here in this picture, you can see this represents the nucleus, and here you have electrons in, well, suppose they are in orbits. You know that this is not exactly that way. But in order that you understand, the inner electrons are the ones that we call core electrons. And the outermost electrons are the one that we call valence electrons, are the ones that are important in chemistry because they are the ones that participate in the chemical reactions. Remember that the valence electrons are the outermost electrons, and they participate in the reactions. Let's continue. Let's continue then by electron configuration.
Electron configuration Z greater than 18. Electron configuration describes how electrons are distributed in orbitals. Rules used. Aufbau principle, electrons fill the lowest energy orbitals first.
Okay, look at this. We are going to study the Aufbau principle, and it says that electrons fill the lowest energy orbitals first. For example, which one is the lowest? The 1s. Then, if you have 2 electrons, you put 2 electrons here. If you have more electrons, you continue to the 2s. If you have more electrons, then you go to the 2p. That remember that the s orbitals only allows 2 electrons, but the p allows until 6 electrons, d until 10, and f until 14. Then you begin here. For example, if the atomic number of the compound is 6, then you begin by here, you say I'm going to put 2 electrons in 1s. And then you come here and you say, oh, I will put 2 more in the 2s. And after that you return, you say, oh, then I go to the 2p. The 2p allows 6, but I have only 6 electrons. Then how many more I can put? 2 and 2 and 2. Then this is the the electronic distribution for an element with atomic number equal to 6. And this diagram that is here is according with the Aufbau principle, where the electrons fill the lowest energy orbitals first. Look, this is the first, this is the second, this is the third, and so on. You have to fill the electrons following the level of energy, the increasing level of energy. Okay, the principle of Aufbau is very, very important. Okay, stop the video. You can make this graph in order to do the exercises. Look, here you have the electronic distribution for sulfur, that is 16. Then you begin 2s2, 2s2, 2p6, 3s2, and then 3p4. And when you add all these electrons, you will get 16. Then this is the electron configuration for sulfur. Let's see. The other important concept is the Pauli exclusion principle. What does it mean? That the spin of the electrons in the same orbital must be opposite in order or antiparallel in order to lower the repulsion between them, because both are negative and they repel each the other. But if they are spinning in opposite direction, this repulsion is low, very low. Now let's go to the Hund's rule. Let's see.
Hund's rule, electrons occupy to generate orbitals singly first. For elements beyond z equals 18, d orbitals begin filling. Exceptions exist, e.g., Cr, Cu. 13. Periodic trends and atomic properties.
Okay,
The
let me stop into here. For example, you begin feeling, before you begin pairing, you have to put at least one electron in each of the orbitals. You cannot begin pairing. This is incorrect. Or you cannot put with opposite spin here than here. All the spins at the beginning are the same, in the same direction. Then when you have the one electron in each orbital is then, if you have more electrons, that you can begin pairing. That's why I told you in this exercise that this is incorrect, this is incorrect. This is the correct answer. Okay? Let's go, and now we go to the periodic trends and the atomic properties. Let's see.
Periodic trends and atomic properties. The periodic table shows regular trends due to electron structure. Major trends. Atomic radius. Increases down a group. Decreases across a period. Ionization energy. Decreases down a group. Increases across a period. Electron affinity. Generally, it becomes more negative across a period. Metallic character. Increases down a group. Decreases across a period. These trends arise from nuclear charge, shielding, distance of valence electrons from the nucleus.
Okay, here you have in this table the behavior of the periodic properties. Ionization energy increases to the right. Electronegativity increases to the right. The atomic radius increases to the left. The electron affinity increases to the right. The atomic radius increases down and decreases up. The electron affinity increases up. The electronegativity increases up, and the ionization energy increases up. So, if you compare one element here with one element here down, according with the metallic character, you will say that the elements here in the first group and down are the most metallic, while the less metallic are to the right and up. And the non-metallic is the opposite. Well, take into account this table, these trends, and you will have questions from here. Let's see.
Atomic structure explains why elements behave differently. Quantum mechanics replaces simple pictures with probabilities, and the periodic table reflects the underlying electron architecture of matter.
Okay, this is the conclusion of this lecture. Please stop the video, watch it again so many times until you learn how to answer questions from here. See you in the next lecture.